We tend to think of the universe as a clockwork system governed by the macroscopic laws of classical physics. It's a reality where gravity guides massive celestial bodies along predictable, deterministic paths. But by the early 20th century, the mathematics of relativity itself allowed for something bizarre, an object so dense it would literally tear the fabric of space-time. Even Albert Einstein believed this was just a mathematical myth, convinced nature would never actually allow such a crazy object to exist. That assumption held until December 1970, when NASA launched a small satellite named Uhuru off the coast of Kenya. Uhuru was built to observe high-energy X-rays that our own atmosphere blocks from human eyes. Buried in the data it sent back was a powerful X-ray source in the constellation Cygnus. It was the first physical observation of a real black hole. We had to accept that these things are actually out there. Some are truly monstrous, holding millions or even billions of times the mass of our own sun, sitting quietly at the center of most large galaxies. And when they interact with their surroundings, they are terrifying. A black hole possesses a gravitational pull strong enough to rip apart and devour whole planets and stars. The defining feature of this destructive power is the event horizon, a definitive physical boundary where the gravitational pull effectively becomes infinite. Approaching this boundary triggers a strange physical effect known as gravitational time dilation. Because the black hole warps the surrounding fabric of space-time so severely, gravity gets exponentially stronger the closer you get. As a direct result, the actual passage of time slows to a crawl compared to someone observing from a safe distance. According to the classical laws of physics, the event horizon is an absolute limit. Once any object passes that boundary, it is on a one-way trip to oblivion. Nothing, not even light, can ever escape. That rule seemed unbreakable until 1974, when physicist Stephen Hawking proposed a theoretical flaw in this one-way door. To find it, he had to stop looking at massive planetary bodies and apply the physics of the incredibly small. He zoomed all the way down to the subatomic realm to examine the true behavior of completely empty space. Quantum mechanics reveals that a vacuum is never truly empty. Instead, it is seething with possibility. Thanks to quantum fluctuations, tiny pairs of particles and their exact opposites, antiparticles, are constantly popping into existence out of nowhere. Under normal conditions, they dance around each other for a fraction of a second and then collide, annihilating each other back into empty space. This chaotic cycle of creation and destruction happens continuously everywhere in the universe. It completely breaks the classical idea that a void is just a static, empty stage. Hawking realized there was a loophole. What happens if a quantum fluctuation occurs right on the razor edge of a black hole's event horizon? In that split second of creation, the immense classical gravity of the black hole overpowers the quantum dance. It yanks one of the newly formed particles across the boundary, trapping it inside forever. But the partner particle is left stranded on the outside. It no longer has anything left to annihilate with, so it simply shoots away into space. If you were watching this from a safe distance, you wouldn't see the complex quantum split. You would just see the black hole itself emitting a particle. This process is known as Hawking radiation. It proves that the probabilistic rules of the quantum world can force the universe's ultimate one-way door to leak energy. That energy leak carries a massive consequence. Because of the conservation of mass, a black hole emitting radiation without consuming new material to replace it is steadily losing mass. Without a constant diet of stars and gas, the black hole actually begins to shrink. It is an agonizingly slow process. For a supermassive black hole at the center of a galaxy to completely evaporate, it requires a time span far longer than the current age of the entire universe. We used to view these objects as indestructible, eternal features of the cosmos. Now we know their true destiny is to quietly evaporate into absolutely nothing. The most violent gravitational forces in nature are ultimately dismantled, piece by piece, by the probabilistic rules of quantum mechanics. While it will take eons for us to observe a black hole fully evaporate, we don't have to wait to study them. We are actively using quantum technology to measure these massive objects right now. Down on Earth, facilities like LIGO operate specifically to listen for the gravitational ripples caused when these dark giants collide. LIGO achieves this through laser interferometry. By relying on the perfectly synchronized quantum behavior of photons inside a laser, the observatory can measure fluctuations in spacetime that are a fraction of the width of a human hair. In 2015, this equipment detected the merger of two massive black holes, a collision releasing more power than all stars in the universe combined. The cosmos is an intricate battleground of scales. Understanding the bizarre, microscopic rules of the quantum realm is giving us the exact tools we need to decode the fate of the largest behemoths in space.